Now, in a previous video, we looked at how to find partial derivatives, implicit partial derivatives, and implicit differentiation in general using essentially the definition, the way that we learned how to do it with the chain rule back in Calc 1, but now applied to three-dimensional problems. But now what we're going to look at in this video is how to actually find those implicit derivatives, but with a shortcut using partial derivatives. Now, I do want to caution students in general, this process is much easier, but you may still be expected by your professor to know how to do it the other way. So learn both ways. Once you get out of this class, of course, you can do it whichever way you want, but typically in multivariable calculus, you may have professors that actually want to see it the other way as well as this way. I often refer to this way as the shortcut way, but it is finding implicit derivatives with partial derivatives. Now, essentially what we're going to do, the idea here is we're going to make a function, an extra variable. We're going to call the function big F, and it's going to be a function of two variables. We're going to create it by putting all of our terms on one side of the equation so that it's equal to 0. And then our big F function will be all of those terms. So in our two-dimensional case where we had only two variables, I just moved the cosine y over to the other side. And so this becomes my function. And then I'm going to need to find the two partial derivatives for this function for both x and y. Now, remember, now that we've been doing the implicit one, partial derivatives, we're going to just take the derivative for x normally, treat y like a constant, and vice versa. When we do the derivative for y, treat y normally, treat x like a constant. So our derivative with respect to x, this is going to be 3x squared, xy will become minus y, and then y squared disappears and cosine y disappears. When we do the partial derivative for y, x cubed disappears, this becomes negative x, this becomes 2y, and this becomes sine y, the sign change. Then the implicit derivative, dy dx, is equivalent to the negative of the partial derivative for x divided by the partial derivative for y. Now, it's important to make a very clear note here. If you're doing dy over dx, you actually need the partial for x on top and the partial for y on the bottom. The order of division with the partials is the reverse of what it was in the dy dx notation. So just be aware of that. Plus, there's this negative sign. So the alternative notation is f sub x over f sub y, and again, flip the sign. And you actually can see that you get the exact same answer, dy over dx. We had 3x squared minus y, that's right here. And we also have negative x plus 2y plus sine y. And again, you can kind of rearrange these. If you put the minus sign through, for instance, you get this. If you rearrange the terms, you will get exactly the same expression that we had in our previous example. Again, the only difference here is that the terms are in a slightly different order. If you were doing the algebra and you moved your dy dx to the other side of the equation, then to match your previous answer, you might need to put the negative sign through the numerator instead, but really you end up with the same answer either way. They're algebraically equivalent. Now let's look at this in the 3 and 4 variable cases. So in general, if you did this in the 3 variable case, you would have the partial derivative for z with respect to x would be the big F partial derivative for x over the partial derivative f with respect to z, and then again the minus sign out front. If you're doing the partial derivative for y, it would be del f del y over del f del z, again with the minus sign. If you're doing the four variable case, again, W is your function. So F sub W is going to go in all the denominators. And then in the top, you'll do your function. Again, this would be now a 5 variable case because there's 4 F, X, Y, W, or X, Y, Z, W, and then the function. So the function for X, again, every one of these formulas has a negative out front. So we could redo the previous example that we had done in the prior video with the 3 variable case. But you would see if you do this process, the partial derivative of F, again, F is itself, put everything on one side of the equation, divided by the partial derivative for Z, and then plug the negative sign in. You should get exactly the same answer that we had in the previous video.